Hello, what is going on? Question 2, SAC 1. In this question, the part A is asking you to find the what? Find the heat of combustion of this fuel or methanol in kilojoules per gram. Normally, when you ask to find the heat of combustion, in most cases, it is delta H of a fuel kilojoules per mole. That's what most questions are going to be based on. In this case, Q is the energy released by the fuel divided by the number of moles of the fuel. You know that, right? You know how to do a questions like that. But this question is little bit strange. Not difficult, little bit strange. You know that this equation is in the data booklet. However, though, using this equation, we will not be able to find the energy released kilojoules per gram. So I'm going to show you another equation you could do. Just a little bit of a variation of this. In that, delta H kilojoules per gram. To do that, to find the delta H in kilojoules per gram, what you need to do, you find the Q fuel in kilojoules. You find the Q fuel in kilojoules, right? Divided by not the number of moles, but the mass in grams. Simple. Mass in grams, right? So that's the equation we are going to use. Sorry about the mess here. So delta H is equal to Q over Q of the fuel. Q of the fuel is the amount of energy released by the fuel, in this case methanol. Mass of, what is mass? Mass is the amount of fuel that got burned in releasing that energy. Okay, so you just find the Q, find the mass in grams, then you get the answer in kilojoules per gram. All right, now let's walk through the question. Okay, so what's happening? What's happening here? We burnt methanol. Using that heat, we have heated the water. The water is going to tell us amount of the energy that is absorbed from the fuel. So amount of energy the water absorbed, we say Q water. Amount of the energy the fuel release or fuel releases, we call it Q fuel. Okay, now what are we trying to do? We are trying to find out the Q fuel, so we can plug that Q fuel value to here. However, you know that we will not be able to measure the Q fuel without water. Water is our friend. Water is going to tell us how much energy has come from the water. Is that clear? So what do we need to do? First, we need to find out the amount of energy the water absorbed, which is Q water. Let's find the Q water. So that's not that difficult to find the Q water. Right, okay, so let's do it here. Oh, let me get that Q water. Q water, you know your favorite cat, M cat. However, though, it is M mass of the water, specific heat capacity of the water, and temperature change of the water. Nothing else, the water. So I'm just going to use MCAT straight away. I hope you understand how to use MCAT, which is 250 grams. 1 milliliter is 1 grams, right? So 250 grams. With the new study design, 1 milliliter, 1 gram. Okay, times by what? 4.18 specific heat capacity. Temperature change is the difference between increase by 23. So 23 goes here. So then what is that value? You got the value as 24035 joules. Always remember, when you use QMCAT, the energy is going to be in joules, not kilojoules. All right, now you have to convert into kilojoules. That is what I was going to say. All right, so which is how many significant figures? This is 3 significant figures, so we'll leave it for 2.40 kilojoules. Okay, now we got the amount of energy absorbed by the water. Now you know your magical assumption we are going to do. What is the magical assumption we are going to do? Important assumption. We are going to assume, even though this is not correct, we have to assume that Q fuel is equal to Q water. So we are assuming all that energy released by the fuel has gone into water, which is not correct. We'll look at that later. So therefore Q fuel is going to be equal to 24.0 kilojoule. Now we got that right. Okay, now we got this right, so this is done. Now no, I was meant to say this is right. Then we need to find the mass of the fuel burn. Mass of the fuel that produced this much, or 24 kilojoules of energy. So how do you find the mass of the fuel, or mass of the methanol burnt, right? Used or burnt. Let's say used, which is going to be the difference between initial mass and the final mass. You are starting with 15.33 grams, and at the end of the experiment you will end up having what? 13.78 grams. So the mass of the ethanol burn is 1.55 grams. Okay, now we got both the values needed for us to find the heat of combustion in what? In kilojoules per gram. So I'm going to do it here. Therefore delta H heat of combustion in kilojoules per gram, which is going to be 24.0 kilojoules divided by 1.55, right? 1.55, which is going to be equal to 15.5 kilojoules per gram. Kilojoules per gram. Now delta H values, this is an exothermic reaction, heat of combustion, it's a negative value. So let's put this value as delta HC, heat of combustion, as minus 15.5 kilojoules per gram. Right, that's it. Let's talk about the heat loss. In a perfect world, all the heat from combustion will heat the water, but in real world some of that energy will escape. Question is asking us to find the percentage heat loss. In order to do that, you need to find out the theoretical heat of combustion and the experimental value, which we have already found. The difference between those two values is the heat lost. Once you know the heat lost, we can find out the percentage heat lost without any problem. Okay, so what's the first thing we need to do? We need to find out the theoretical delta HC value. Now in the data booklet, that value is not given to you in kilojoules per gram. The theoretical value for methanol is given to you in kilojoules per mole. So our first task is to get the heat of combustion of methanol in kilojoules per gram. to do that, what you need to do, get the data booklet value. I would say delta HC, let me say theoretical value is going to be equal to in kilojoules per gram, right? Now data booklet has got this value 726. 726, that's the kilojoules per mole. To find out that value, I would say this is kilojoules per gram. So we are trying to find out the theoretical delta H value in kilojoules per gram. In order to do that, you need to divide 726 by methanol molar mass. Methanol molar mass is 32.0. So you get that value as 22.7 kilojoule per gram. Okay, that's that value in kilojoules. Oh, where's the kilojoules? Kilojoules per gram. Okay, right. Now in our previous part of this question, we have found the experimental experimental value, delta HC experimental. We have found it already, remember, which was 15.5 kilojoules per gram. Now what we are going to do next, we are going to find out the heat loss in kilojoules per gram. So therefore heat lost we can work that out. 22.7 minus 15.5, so the answer is what? 7.2 kilojoules per gram. So we have found out the heat loss in kilojoules per every gram. Now it is easier for us to find the percentage heat loss. So percentage heat loss is going to be equal to what? Heat lost, which is 7.2 kilojoules per gram. I can even write kilojoules per gram here. Oh, where's the joules, man? Okay, kilojoules per gram divided by the theoretical value, which is 22.7 kilojoules per gram times 100. I say percentage heat loss. It's not writing for some reason. Percentage heat loss, which is going to be equal to, I think, somewhere around 31.9. Somewhere around 31.9%. So as you can see, 31.9% of heat from the fuel has lost into the surrounding. Is that clear? All right, I'll see you soon. So let's look at the question part B. These are, both of them are worded questions. There are no calculations. Right, I know most of us find it difficult to answer these worded questions, right? Now, the first part of this B1, okay, a windshield is used in the setup. Have a look at the previous diagram. You will see the windshield around the flame, okay? Explain the purpose of the windshield and its effect on the precision of the experiment. Now, windshield has got one clear job: to prevent the heat loss. By preventing the air currents, it ensures that most of the energy from the flame goes into water rather than going into the surrounding. Okay, by doing so, you will also end up getting consistent results between trials, because you pretty much end up losing the same amount of heat for each trial. That will enables you to get results with certain consistency. Consistent results means precision. So it will increase the precision by preventing heat loss, or it enables the system to lose heat same amount for each trial. Thereby it will increase the precision. So in order to get those 2 marks, firstly you need to say the function of the windshield, then you need to link the function to precision, how it can improve the precision of the experiment. Precision is all about getting consistent results. That's what precision is. So in other words, you are trying to minimize the random errors. Okay, now I will write a proper answer in the description. Let's look at the next part. I think this should be part B1 and this should be part 2. 2 marker. The windshield is placed completely surrounding the spirit burner suggests a potential disadvantage. Using a windshield and explain the effect. Another 2 mark. Final molar heat of combustion. Okay, now what will happen here? As you know, every solution comes with the trade-off. Having this windshield completely surrounding the flame can block oxygen coming into the flame. So what happens? You don't get enough oxygen, means incomplete combustion. Incomplete combustion releases lower amount of heat to the water. So then what happens? Let me write that here. When you have lower amount of heat going into water, what will happen? Listen, delta T of the water, temperature change of the water, is going to be lower. Since the temperature change of the water is going to be lower, you use Q MCAT to find the energy absorbed by water. In other words, Q water is the value for the Q water is going to be lower. Q water, therefore Q fuel is also going to be lower, because in this calculation we make assumption. What is the assumption? Q water is equal to Q fuel. So now we have a lower Q value for the fuel. Now final point. So how is that going to affect the delta H? Now you know that delta H is equal to Q fuel over the number of moles of the fuel. Then what happens? Due to this, you will end up getting lower delta H value. Lower delta H value. Then again, I will write a proper answer in the description, okay? But get the idea, okay? You cannot memorize these answers, but you need to understand what's going on. It's not that difficult. Having a heat shield, less oxygen coming in, incomplete combustion, lower energy is released. During incomplete combustion, low amount of energy is released to the water. So the temperature change of the water is going to be lower. So Q water, for our calculation, we find out Q water is going to be lower. Q water is going to be lower means Q fuel is also going to be lower. Therefore, delta H is also going to be lower.